a video of an experiment on active pneumatics. I'll be returning to this later in the talk. But for the moment, I'd just like to point out that my general interest is in nonlinear dynamics and chaos, which is a very broad field that can be applied to many different subfields of physics. And so I just wanted to mention some past work, I'm not going to be talking about this, that I did on Bose-Einstein condensates because it does fit into the theme of this conference and the wonderful impact that Bose's work had on my own research trajectory. So there are a number of cases where you can see beautiful chaotic behavior in BECs as well. But now I'd like to turn my attention to collective matter, or collective motion and active matter. This is really a hot topic in soft matter physics these days. And I'm showing several examples of systems that are either materials or that can be roughly thought of as a kind of material. These are classic examples of active motion, active matter. So here we see a flock of birds that forms this, what's called a murmuration, this pattern that they form. Or, let's see, there's other videos here. Why are they not going? Here we go. All right. Of course, you have similar motion in schools of fish. This is a slime mold. And down here, this is the mitosis process where microtubules are being pulled or are pulling apart chromosomes during cell division. And this is actually closer in spirit to what I'm going to be talking about in this talk. But in all of these cases, what you have is you have energy that's injected at small scales that gives rise to large-scale coherent motion. That's the general theme of active materials. And my particular take on this, because I come from the world of chaotic dynamics, is I study these systems by applying tools from chaos theory, in particular chaotic transport. So these are tools like Lyapunov exponents and some other measures of chaos like topological entropy that I'll be talking about later, and applying these to experimental measurements. I should mention that I'm a theorist. All of the experiments I'm going to show here are done by a colleague of mine. But I apply these theoretical tools to experimental measurements and sometimes to simulations as well. So what is the particular system that I'm interested in discussing today? It's a beautiful system. And it's extremely simple. You begin with microtubules, which just think of them as little rods. They're rod-like molecules. They're in every one of your cells. And they tend to align in what's called a pneumatic phase, where all the microtubules kind of align up, assuming they're at a high enough density. And in this case, they are also cross-linked by molecular motors, in particular a kinesin motor. Now, these molecular motors, I'm going to use my hand here. So my arm represents the microtubule, and the motor tends to walk along the microtubule from the negative end of the microtubule to the positive end of the microtubule. This is a geometric polarization, so there's a geometric distinction between one end of the microtubule that we call the minus end and the other end that we call the positive end. It's not electrically charged. But anyhow, these kinesin motors walk along the microtubules, and you can put two of them together where their heads are stuck together and their feet are dangling like this, and the feet will then cross-link between the microtubules, shown here. And if the microtubules are anti-aligned, then one pair of feet is walking downwards, the other pair of feet is walking upwards, and what you can imagine is happening is that's causing the microtubules to slide relative to one another. So that's really the important takeaway here, is that these microtubules are sliding, there's a shearing between them, and that's causing an extensile behavior in the material. So what you can do is you can make a two-dimensional layer at an oil-water interface a very high density layer of these microtubules. And this is what you get here, shown in green. Okay, it's this beautiful chaotic advection pattern of this high density of microtubule bundles that are being driven by, I didn't mention this before, but the molecular motors are driven by ATP, adenosine triphosphate, which is the fuel system of your cell, right? It's the fuel system of biology. And you get this beautiful behavior here. Now, this system was pioneered by Zvonimir Dojic, who is currently at the University of California, Santa Barbara, a little over a decade ago. And there's been a lot of work on this system. This particular video was taken in the lab of Linda Hurst at UC Merced, which is where I'm from, by her student Amanda Tan. Okay, so being somebody who's interested in chaos, as soon as I saw this kind of data, I said, this is a system that I have to study. It's just too beautiful. I couldn't walk away from it. And that's led me to the talk that I'm giving here today. Okay, suffice it to say that many people have been looking at this system over the last decade plus, putting it in different geometries, applying external fields, and pushing and prodding it in all sorts of different ways. So there's a large body of research on this particular system. I'm going to be telling you two stories, time permitting. The first is a story about how these systems are stirred. And this is really a story about topology. We've heard a lot about topology at this conference. And so there'll be quite a bit of topology in what I'm going to discuss here today. Okay, so the first things first, we notice that there's a particular local order within this system. It's what's called nematic ordering, and it's given by these arrows. Now you notice these arrows have two heads to them, right? So if I take one of these arrows and I rotate it by 180 degrees, it's the same arrow. And this symmetry, we call such an arrow that has this symmetry a director. So rather than calling it a vector, we call it a director. And a director is just a vector where you don't distinguish between the head and the tail. Okay? And so as we move throughout this fluid, we see that the director is changing its orientation. It's just a local symmetry of the system. And then you'll also see that there are these voids, places where the local order is not defined, and these form topological charges. And we've seen examples of this actually earlier today. Whoops. Okay. Just one moment. There we go. And these topological charges come in two flavors here. What's called a +1/2 defect and a -1/2 defect. The +1/2 defect has the geometry of this kind of hairpin turn. The -1/2 defect has this sort of threefold geometry. So why is it called a +1/2 defect? Well, if I go up here to the top and I point an arrow to the right, and then I follow the director as I move clockwise around this defect, what happens to the vector? The vector also rotates clockwise, and it goes half a turn. So I do one full circuit in the clockwise direction. The vector does half a circuit, also in the clockwise direction. That's why it's called +1/2. And I should note that because we have this nematic symmetry, a vector pointing to the left and a vector pointing to the right are really the same. Now, down here for the -1/2 defect, if I do the same thing, I begin with, in this case, a vector pointing upward, and I go clockwise around the defect. The vector rotates a half turn in the counterclockwise direction, so that's why it's called -1/2. Now, topological charge, just like electric charge, is conserved. So these defects can be created, they can be destroyed, but only in pairs, plus and -1/2 pairs. And so, here's the video of the motion of the defects. You can see these defects moving around. You'll see them being created and destroyed, but always in pairs. Okay, so this is the basic system we want to study. And I'm going to take a little bit of a detour and talk about topological stirring at low Reynolds number. Low Reynolds number means we're thinking about systems that are either very, very viscous, like imagine a vat of honey or a vat of very viscous paint or tar, or they're at very small scales, like microfluidic systems are also at very low Reynolds numbers. And this is an experiment that was done as a kind of illustration in the lab of Mark Stremler some years ago. And they took this, what's basically kind of a little petri dish filled with fluid, and they wanted to mix it. And they did the following protocol. They put 3 rods into the fluid, and in the first step, you rotate the right 2 rods in the clockwise direction. And in the second step, you rotate the left 2 rods also in the clockwise direction. And then you repeat that pattern. And this is what you get from the experiment. If you put these lines of dye to track the fluid, you see that the fluid gets mixed after each period of this mixing protocol, but it's not very well mixed by the end. This is not a particularly good way to mix the dye. And the reason for that is that the length of these lines of dye is growing only algebraically in time, and we'd really like to see exponential growth. Now, we can describe this protocol with the following space-time diagram. So here, each of these circles represents a rod, and we see the trajectories of these rods as we move upwards in time. And these trajectories braid around one another. Here's the first swap, here's the second swap. And so each of this protocol we can describe by a mathematical braid. Okay. Now, they did a similar experiment using a different protocol that is very, very similar to the first. The only difference between these 2 protocols is where in the first protocol, the second swap was in the clockwise direction. In the second protocol, the second swap's in the counterclockwise direction. Everything else is the same. So we swap once in the clockwise direction, once in the counterclockwise direction. But notice the tremendous difference in mixing that we get. By the time we get down here, the system is very well mixed. I mean, there's a boundary effect here, but look at the center. The center here is very well mixed compared to the first protocol. And that's because we actually have chaos. We have chaotic advection in this system. And these lines of dye are being stretched exponentially in time. Similarly, we have a different braiding pattern for this protocol. And so the moral of this story is that it's not just the number of stirring rods or the speed of the stirring rods that's important. It's also this global topological manner in which the stirrers braid around one another that's crucial to the degree of mixing. Okay? So now I'd like to return to the active pneumatic system that we're interested in studying. This is just summarizes what I was telling you on the previous slide. And now I'm returning to the active pneumatic, and I want you to look at this picture here in green. This is the experimental image of the active pneumatic, and compare it to this picture here, which is the dye mixing experiment. Notice that these +1/2 defects have exactly the same structure as the dye around the stirring rods. And so we're going to take that analogy very seriously. We think of the +1/2 defects as being like stirring rods that are mixing this active pneumatic system. But there's a very important distinction. In the case of stirring rods, what are you doing? You're moving the rods, and that causes exponential stretching in the fluid. In the case of the active pneumatic, the ATP is driving exponential stretching in the fluid, and the defects, which we're thinking of as rods, are moving in response, right? So it's a question of what is you're controlling and what is responding. Okay. That said, we conjectured that all of the mixing of this active pneumatic system you could think of as being driven by a kind of virtual stirring by the defects. And in order to make this idea precise, we need some measures of chaos. We need some measures of how well the mixing is taking place. The first of these is the most famous measure of chaos, the Lyapunov exponent. A Lyapunov exponent just describes how quickly two nearby trajectories diverge from one another. Okay, it's an exponential divergence rate. And you can compute the Lyapunov exponent in this system. There's a little mathematical theorem that says what you can do is you can look along the microtubule bundles, which I'm showing here in green. N is pointing in the direction of the director. It's telling me the alignment of this microtubule bundle. And if I compute the velocity gradient, so this is the gradient of the velocity, and I take the double dot product along the microtubule, and that basically is telling me the stretching rate along the microtubule bundles, and I average that over space and time, that will give me the Lyapunov exponent. Okay? And so we can find the velocity field from the experimental movie. There's a lot of details here, but at the end of the day, we get a Lyapunov exponent, which is telling us something about the degree of mixing of the system. And this number by itself is kind of meaningless, right? This is just one little dot hanging out here. The one thing I do want to point out is that the Lyapunov exponent has units of inverse time. It gives us a time scale. So here it's inverse seconds. Okay. Well, now to give some context to this one data point, we need to get a few more data points. And so the next thing we're going to look at is what's called the topological entropy. This is closely related to the Lyapunov exponent, but is a different kind of animal. So here in this simulation that I'm showing down below, I'm imagining that we're stirring some dye, and this blue line that you see, the one that's moving, is the line of dye that's getting stretched. And we can look at the length of that line as a function of time, and it's growing exponentially. The Euclidean length is growing exponentially. That growth rate is the topological entropy. So the topological entropy is the growth rate in the length of a material line, like dye, as you stir the fluid. Okay. And you can measure this in the experiments by embedding beads within the fluid and then connecting the bead, like a pair of beads, along the director. That's this blue line. Amanda Tan did this. She did it all by hand, actually. And you plot the length as a function of time. You'll see it grows exponentially. In a semi-log plot, that's a straight line. The slope of this gives us the topological entropy. Okay, so we can put that up here on the board, and we see that the topological entropy, which also has units of inverse time, can be compared to the Lyapunov exponent, and they're very close to one another. Okay? Now, there are other ways you can measure the topological entropy. To put a few more data points up here, you can, instead of looking at beads, you can look at the plus and minus 1/2 defects themselves. So that's what's being shown here. And again, this curve connecting them is growing exponentially in time. The slope here will give us another way of measuring the topological entropy. And so let's put that up on the board. And that's what we get here. Now, it's exactly the same as we got for the bead experiment. That's actually kind of remarkable. What it's telling us is that the defects are moving as though they're just passive tracers in the fluid. Okay. Finally, we have a sort of a more topological way of computing the topological entropy, which doesn't require any sort of Euclidean length whatsoever. And here's the way to think about it. Each point here represents one of these defects. Okay, so you can imagine that these are like stirring rods that are put in the plane. And then between the points, imagine that you have a grid or a triangulation, which is a kind of elastic mesh. Okay, it's mathematical, of course, but you can think of it physically as being a kind of elastic mesh. And as these points move, they'll stretch this mesh and they'll cause the mesh to fold over on itself. So let me show you the animation. I mean, this is taken from real data. So we see here that every time one of these defects strikes a band, it doesn't pass through the band. It causes the band to turn to bend and fold over on itself. And so we can just count the number of these segments as a function of time. And what do you think that's going to give us? Well, that's going to give us this exponential growth. Let's focus on the black line here. This is where we're effectively stirring the fluid just from the positive defects. Okay, so we're just using the positive defects, not the negative defects. And this line is giving us a topological entropy shown here. Now, if I just stir the fluid by the negative defects, I imagine that I just put rods at each of the negative defects and stir the fluid that way, I get this green line, which is a lower slope. So not surprisingly, the positive defects stir the fluid more effectively than the negative defects. But what's really important here is if I use both positive and negative defects. So I take this black line and I throw in all the negative defects. I double the number of stirring rods. You might imagine that you get a lot more mixing. But in fact, it's exactly the same. You get this blue line here when you add in the negative defects to the positive defects. So what this tells us is that the negative defects really don't add any entropy, any topological entropy to the stirring that you already get from the positive defects. So the positive defects are really doing all of the stirring. And that really confirms part of our conjecture that all of the mixing in this system is due to this kind of stirring by the positive defects alone. Okay, well anyhow, if you compute the topological entropy, I've now walked you through 3 different ways of computing topological entropy. They all agree with one another, and they're actually a little bit larger than the Lyapunov exponent. But this is good. We expect them to all be roughly the same. I'll just mention that you can do different experiments at different levels of ATP, which cause the system, so the more ATP you put into the system, that's like putting more fuel into the system, roughly speaking, goes faster. So you have this upward trend here. And in every one of the cases, the Lyapunov exponent is slightly below the topological entropy. And that might just be an experimental quirk, but there is actually a theorem here. This is a well-known theorem in dynamical systems that says for these kinds of two-dimensional fluid problems, the Lyapunov exponent is in fact bounded by the topological entropy. So we would have been really concerned if this was flipped. If the black dots were above the red dots, that would have been a problem. But with the black dots being below the red dots, that's actually consistent with this mathematical theorem. Okay. Okay. So just to summarize the first part of the talk, this sort of local extension of active pneumatic forces gives us a kind of coordinated global braiding of +1/2 defects. And you can use topological techniques to compute the topological entropy, and you can also compute the Lyapunov exponent, and you find that these quantities are consistent with one another and in fact close in value. Okay, so this was kind of an old story. I'd now like to move on to something a little bit newer, which is how you can control the motion of these defects by engineering the boundary. How much time do I have left? 10 minutes, perfect. Okay, so one of the things that Dogic did in his lab a number of years ago was to confine an active pneumatic in a circular disc. And this is what they found. Roughly speaking, you have 2 +1/2 defects that move around one another in kind of like a yin-yang pattern. But then every so often you have a third defect come in from the boundary, trade places with one of the other 2 defects, and then undergo that same pattern. So this is what's called the doubly periodic braiding. Here's another incursion here. So you have 2 defects most of the time, but occasionally a third defect comes into play. And so why does that happen? Well, we have a particular interpretation which is topological in nature. First of all, topology tells us on the circle that you have to have 2 +1/2 defects inside. But you can't get any topological entropy by just braiding 2 defects around one another. That doesn't give rise to exponential stretching. And we have exponential stretching in this system. The minimum number of stirring rods that will give you exponential stretching is 3. So you have to have a third defect come in. There's no other way around it. The topology tells you that exponential stretching requires 3 defects. And so that's our topological explanation for why you have this incursion happening. Okay. Suffice it to say, there have been others who have studied active pneumatics confined to circles. I think in the interest of time, I'm going to skip over that. You can see the pretty pictures here. But I want to jump ahead to what we did, which is we were asking the question of, can we get just purely periodic motion of defects in this active pneumatic system? And we know that that's going to require us to have 3 plus 1/2 defects. That's the minimum number. So how do you engineer the boundary? Well, we already saw that if you have a circle, the circle has a topological charge of +1, and there's a kind of Gauss's law that says whatever the charge, the topological charge of the boundary is, you have to have at least that many plus 1/2 defects inside, plus 1/2 defects, right? So for a boundary charge of 1, we need 2 plus 1/2 defects, because 2 times 1/2 is equal to 1. Okay, but we want 3. So what we can do is we can engineer the boundary so it has this cusp here. And this cusp changes the topological charge of the boundary to be 3/2. That means we have to have at least 3 plus 1/2 defects inside. That's exactly the number we want. You could, of course, keep going. You could put 2 cusps, and that would give you 4 defects. But 3 is enough. So this is the kind of pattern of defects that we want to see. So Linda had another very good student, fresh to mammarian, who did the experiment. And after, this took a lot of work. As a theorist, I can just sort of put the experimental results up and it looks nice and easy. But I can attest that a lot of work went into this. You have to tune the size of this cardioid just right. And it's really hard to get the material into the well. Nevertheless, she succeeded. And what did she find? Here we have exactly the 3 defects. And let me show you. This is what happens as a function of time. These defects braid around one another, and no defects are created, no defects are destroyed. You get 3 defects, as far as we know, for all time here. Okay. And this sort of cardioid or heart shape shows up in a lot of examples of mixing at high viscosity. Here's a taffy puller. You can see it in baked goods. Here's that stirring rod of, or the dye experiment I showed before, and this is the active pneumatic system. Okay, so what braid are we actually seeing? I apologize, this is a little hard to see in this room, but let me show you what we have here. We have these, I chose a time where these 3 defects are all in a line. And what happens is the bottom 2 defects switch places in the clockwise direction. Then the top 2 defects switch places in the counterclockwise direction. Well, that should be familiar. That's exactly the stirring pattern that I mentioned before. You have a swap in the clockwise direction, a swap in the counterclockwise direction, and then you repeat it. And so this is the space-time diagram showing this braiding behavior. And in fact, this braid has a name. It's called the golden braid. Why is it's actually just the braid that you would use to braid hair. So why is it called the golden braid? Well, it's related to the golden ratio. So one of the beautiful things about this braiding is that it guarantees you have a certain amount of stretching, topological entropy in the system. So if I take a fluid and I braid it, or I stir it using this particular braid, this double swap braid, I'm guaranteed to get a minimum amount of topological entropy, which is twice the log of the golden ratio. So if I just look at one swap, I divide this by 2, and I find that the topological entropy per swap, if you will, is log of the golden ratio. And this is the best you can do. This is the optimal braiding with 3 stirring rods. And so what you can show in this experiment is, in fact, if I track a curve within this fluid, I see that its length grows by exactly the amount that's predicted here. You can look at compression as well. I can look at how this curve here gets compressed against the boundary of the cardioid. And because area is basically conserved in this system, the compression rate and the extension rate are the same to conserve area. And again, this compression rate is exactly what we predict from braid theory. And so this just summarizes, here's the braid theoretic computation, log of the golden ratio. And these are the values that we measure from the experiments. And we did this for 2 cardioids of different sizes. Okay. There's more that can be said as you go to larger cardioids, but I just want to end with my second take-home message, which is that by understanding, an understanding of topological entropy leads to certain design principles for engineering control of these defects. And these experimental results support this claim that you can in fact get just 3 defects moving around one another, forming this golden braid. And it allows you to actually compute the mixing rate in a closed form expression, which I think is just really wonderful. And this work just came out a few months ago in PRL. So here are the acknowledgements. A lot of folks have worked on this with me over the years, especially Linda Hurst, who did the experiments, and her students. And I just want to give a shout out here to Manuel Sabir, who is in fact a student from the University of Dhaka, who's now a graduate student, a PhD student working with me in California. And with that, I thank you for your attention.
For questions? Yeah. Could you turn it on? Turn on the mic.
Can you hear me now?
I can.
Yeah, okay. I want to ask one thing simply to make sure. When you do the experiments, the turning is always in the same direction. The turning. It's not that you shuffle the whole thing. It just goes in one direction.
So it could go in either direction. Okay, so let me make sure I understand which experiment you're talking about. You're talking about this one here.
Yeah.
Yes. Okay, so the direction here is it's always going to be clockwise on the bottom and counterclockwise on the top. And that's because of the position of the cusp right here. Mm-hmm. So that breaks the symmetry.
Because, I heard long time ago, Tabor from the famous paper by Tabor and Berry that if you do in a fluid something like this, and let's say that you take cream and chocolate, so you could follow it. Mm-hmm. So he was saying that essentially, if you turn around, I don't know for how long, because it's a question of the Lyapunov exponent. If you turn around and then you turn back,
yes,
you will go back to the original. I have never seen it at home when I do that.
Right.
Yeah.
Yeah.
So have you seen that in the laboratory?
So if I understand correctly, what you're talking about is this sort of famous result that at low Reynolds number, basically Reynolds number 0, that the system is time reversible. You'll get, if you stir it in one way, the dye will start to mix, and then you completely reverse time, the system will unmix to some degree.
It has to be for the time. It has to be of the inverse of the time given by the Lyapunov exponent, I suppose. If you go very far in time.
That's right. So you can't go indefinitely far in time because of chaos, but also because of diffusion. But we can't do that here because we can't reverse time. The system, because of the basically because of the cusp here, it forces it to go in one direction. It would be interesting to think about how maybe you could, by engineering the system differently, force it to go backwards in time. That's a good question.
Okay, thank you.
Yes.
Okay, thank you very much for very nice talk. This I assume that the temperature was room temperature for all these experiments.
That's right.
So, what is the effect of number of defects or density of defects by temperature? We don't know it.
I don't think I heard the question.
What is the effect of temperature in the density of defects? I mean, number of defects will increase or decrease?
That's a good question. So in this example, it's exactly fixed at 3. But in the bulk behavior,
Yes.
Where the defects are being created and destroyed,
Yeah.
On average, the number of defects is the same. There are, of course, fluctuations, but the spacing between defects is given both by the amount of ATP, the ATP concentration, as well as the elasticity of the material.
So, is there analogy between this type of defects and vortex, anti-vortex in XY model?
I mean, that's a very good question. And I think one that still remains to be answered. I don't want to speculate.
Okay,
But it's something we've thought about.
thank you.
Yes.
So these are two-dimensional models, right?
That's right. This is just two-dimensional.
Biological systems are three-dimensional, right? So it seems to me, intuitively at least, that a lot of the properties of this model are very specific to 2D. And are there some generalizations to higher dimension?
Yeah, that's a good question. So first of all, of course, this is a biologically inspired system. The actual microtubules and kinesin motors in a real cell don't, of course, behave this way. It's engineered. But to get to your question about 3 dimensions, there have been experiments done of similar systems in 3 dimensions. There's no reason why you can't write down a model either in simulation or in the laboratory that's in 3 dimensions, right? So, and in 3 dimensions, instead of point defects, of course, you get defect lines, and they have beautiful dynamics themselves.
Any other question? Okay, if not, then let's thank the speaker.
We had one more, I think,
Oh,
down
there
here.
is.
Kelvin, what I see from your first experiment, that when you start stirring, a chaotic attractor evolves, and then it expands. So it appears like it starts from steady states, and it evolves a small chaotic attractor inside, and possibly you are increasing the rate of stirring. I don't know if I understand correctly. And due to that increasing the rate of stirring, you have an expansion of the attractor. So my question is, what is the route to this evolution of the chaotic attractor? Is it straight from the steady state to the small attractor, or any other route?
So I don't think I would classify this as a strange attractor, chaotic attractor. It's actually something that I'm not presenting here, but that I thought about quite a bit. If you have a closed fluid system, right? So not an open system, but a closed system that is chaotic and area preserving, which the system is, then if you have a line of dye in that system, you don't get a strange attractor because eventually it's going to fill up the entire domain and you're just going to get uniform filling. So in order to get a strange attractor, you would, for a confined system, you can't do it with area preservation because it has to contract onto the strange attractor. It has to be contracting somehow. Now you can get a strange attractor if it's an open system where material is flowing through. There you would get like a heteroclinic tangle kind of structure. Nevertheless, this does have fractal behavior to it. And that is something we've explored. I'd love to talk to you about this afterwards.
Okay, we'll talk to you later. Thank you.
Okay. Thanks very much, Kevin.
Thank you.
Thank you.
Participants, let us move to the poster session. Our last session will start from 4 p.m. So then please return back to this auditorium at 4 p.m. Thank you.